Let us begin with motivation, with the broad idea of structure preservation in measure theory. When we study measure theory, we are not only interested in sets and functions as isolated objects. We are interested in how structure is preserved when we move from one space to another, or when we change our point of view. Very often, the most meaningful maps in analysis are not arbitrary maps, but maps that respect size, shape, and accumulation. They respect what we might loosely call the mass of a set, or the amount of space it occupies. It is helpful to pause and reflect on why this matters. Integration, probability, and expectation are all built on the idea of size. When we integrate a function, we are accumulating values over a region, weighted by how large that region is. When we talk about probability, we assign likelihood based on the size of events. If a transformation completely scrambles size, then integration and probability lose their coherence. So there is a natural desire to identify maps that behave well with respect to measure. These are maps that rearrange space without stretching it or compressing it, at least not in a way that changes total size. Such maps allow us to move between viewpoints while preserving the essential quantitative structure. This idea unifies many Euler concepts. It connects to the way integrals behave under substitution. It connects to symmetry arguments in probability. It connects to the idea that two different coordinate descriptions may represent the same underlying reality. All of this motivates the study of measure-preserving maps. Let us now turn to measure-preserving maps themselves. Intuitively, a measure-preserving map is a transformation that does not change the size of sets. If we take a region of space and move it through such a map, the region may be rearranged, folded, or relocated, but its size remains the same. Nothing is lost and nothing is gained. It can be helpful to think of this as rearranging sand on a table. You may move the sand around, spreading it differently, but if no sand is removed and none is added, the total amount remains unchanged. Measure-preserving maps are like that. They are rearrangements rather than distortions. Concrete examples help. Imagine shifting every point to the right by a fixed amount. The intervals move, but their lengths do not change. Or imagine rotating a shape around the origin. The shape occupies a different location, but its area remains the same. These transformations preserve size. It is helpful to say this again. A measure-preserving map does not care about the exact location of point. It cares only about preserving the size of sets. This is what distinguishes it from an arbitrary mapping, which may stretch small sets into large ones or collapse large sets into negligible ones. By repeatedly contrasting these two kinds of behavior, we sharpen our intuition. Arbitrary maps destroy structure. Measure-preserving maps respect it. They allow us to move through space while keeping quantitative information intact. With this intuition in place, we can turn naturally to integration and substitution. Substitution in integration can be understood as a change of viewpoint. Instead of integrating over one set, we integrate over its image under a transformation. If the transformation preserves measure, then the total accumulated value remains unchanged. This is a profound idea, and it is worth repeating slowly. Integration depends on size, not on labels or coordinates. If we describe the same region using different coordinates, but without changing its size, then the integral should not change. Measure-preserving maps make this principle precise. They ensure that when we pull a function back through the transformation, the total contribution remains the same. This leads to invariance properties that are central in analysis and probability. It is helpful to connect this to symmetry. If a probability distribution is symmetric under a certain transformation, then expectations remain unchanged. This is not an accident. It is a direct consequence of measure preservation. We can pause here and reflect. Measure-preserving maps allow integration to behave well under change. They tell us that integration is fundamentally about size and accumulation, not about the specific coordinates we use. With this settled, we now shift our attention to functions of bounded variation, beginning with motivation. A function of bounded variation is a function whose total amount of change is controlled. Instead of focusing on smoothness or differentiability, we focus on how much the function goes up and down in total. Imagine walking along the graph of a function. Each time the function rises or falls, you accumulate variation. If the total accumulated change remains finite, then the function has bounded variation. This idea sits between regularity and generality. On one hand, functions of bounded variation are more general than smooth functions. They may have corners, flat regions, or sudden changes. On the other hand, they are far more controlled than arbitrary functions, which may oscillate wildly without bound. It is reassuring to know that bounded variation captures a broad class of meaningful functions while excluding pathological behavior. This balance makes the concept extremely useful. Now we turn to one of the most important structural results, decomposition into monotone functions. Every function of bounded variation can be written as the difference of two monotone functions. This is a remarkable statement, and it deserves slow repetition. Monotone functions are easy to understand. They move in one direction only. They do not oscillate. They accumulate change in a controlled way. By decomposing a complex function into monotone pieces, we break complexity into simpler components. It is helpful to say this again from a different angle. Even if a function seems complicated, its complexity can be explained as the interaction of two simpler, orderly behaviors. One pushes upward, the other pulls downward. This decomposition is not merely formal. It reveals deep structure. It tells us that bounded variation is not arbitrary variation, but structured variation. We now move to almost everywhere differentiability. Although functions of bounded variation may not be differentiable at every point, they are differentiable almost everywhere. This means that the points where differentiability fails form a negligible set. This is a strong regularity result. It tells us that failure of differentiability is rare in a precise sense. The function behaves nicely almost everywhere, even if there are isolated or thin regions of irregularity. It is important to contrast pointwise failure with global control. A function may fail to be differentiable at many points in a naive sense, but as long as those points occupy negligible size, the overall behavior remains well structured. This idea appears repeatedly in measure theory, and it is comforting to recognize it again here. Closely related is the idea of termwise differentiability. When a function of bounded variation is decomposed into monotone parts, we can differentiate those parts almost everywhere, and then combine the results. Bounded variation makes this possible by controlling total change. Structure allows controlled operations. Because a function does not oscillate too wildly, differentiation behaves predictably almost everywhere. We move now to absolute continuity and singularity. Absolute continuity describes functions that are sensitive to small sets. If a set has very small size, then the change of the function over that set is also small. Change is spread smoothly and evenly. Singular behavior is different. It concentrates change on sets that are negligible in size. The function may change significantly, but only on extremely thin sets. It is helpful to picture this distinction. Absolute continuity is like pouring water evenly across a surface. Singular behavior is like placing weight on a needlepoint. These two behaviors are fundamentally different, yet both can occur within functions of bounded variation. Repeating this contrast helps fix the intuition. We now address the measurability of the derivative. The derivative of a function of bounded variation, defined almost everywhere, turns out to be measurable. This is not an accident. It ensures compatibility with integration and with the broader framework of measure theory. Measurability allows us to integrate the derivative to analyze its distribution and to connect differentiation back to accumulation. Once again, structure reveals coherence. This leads naturally to the characterization of absolute continuity. A function is absolutely continuous precisely when its change can be recovered by integrating its derivative. This means that all variation is accounted for by smooth accumulation. This characterization ties together sensitivity to small sets, integrability of the derivative, and controlled accumulation of change. It is helpful to pause and reflect on how these ideas reinforce each other. Finally, we reach the decomposition into absolutely continuous and singular parts. Every function of bounded variation can be split into two fundamentally different behaviors. One part behaves like classical integration, spreading change smoothly across space. The other part captures concentrated change that lives on negligible sets. This decomposition is a central unifying result. It tells us that all controlled one-dimensional behavior can be understood as a mixture of smooth accumulation and singular concentration. Let us pause and reflect one last time. Measure-preserving maps show us how structure can be preserved under transformation. Functions of bounded variation show us how change can be controlled and decomposed. Absolute continuity and singularity describe the two fundamental ways that change can occur. Together, these ideas reveal a deep and reassuring structure beneath integration, differentiation, and change. They show that even in great generality, analysis remains orderly, coherent, and comprehensible.